This is a video from section 5.5 found in a Calculus 1 class. We're going to take examples from the Stewart Calculus textbook, 9th edition. Recall, the integral of u to the n du is 1 over n plus 1 u to the n plus 1 plus c, where n does not equal -1. So if I take the derivative of 1 over n plus 1 u to the n plus 1 plus c, remember c is constant, I claim that I will get u to the n back. Number 2, the integral of cosine of u du is sine of u plus c. Number 3, the integral of sine of u du is negative cosine u plus c. Number 4, the integral of secant squared u du is equal to tangent u plus c. So even if you look at number 4, if I take the derivative of tangent of u plus c with respect to u, I will get secant squared of u. So we're looking for a family of functions whose derivative is what we're, like in this case, in number 4, we're looking for a family of functions whose derivative ends up being secant squared u. Okay? Now, with that in mind, let's take a look at some examples. So what I want to do is I want to take a look at problem 14. And by the way, the directions say to evaluate the indefinite integral. So let's again go ahead and take a look at number 14. Suppose I have the integral of secant squared of 2 theta d theta. Now, the inside function appears to be 2 theta. So that's a good candidate for u. And we're doing this by u substitution. Okay? So we're going to transform this integral into something a bit more manageable to integrate. So I'm going to let u be 2 theta. Du is 2 d theta. Okay. Now d theta is 1/2 du. So I really want to stress to you that I'm trying to transform everything in terms of u before we touch this question. So this is the integral of secant squared u du. And then remember, we have a 1/2 on the outside. Because let's review this. Remember that 2 theta became u. D theta became 1/2 du. Now, we just learned that the integral of secant squared u du is tangent u plus c. So the 1/2 is going to go along for the ride, and so this ends up being 1/2 tangent u plus c. But u is equal to 2 theta. So this is 1/2 tangent of 2 theta plus c. That's how we do problem 14. Let's take a look at 17. Suppose I had the integral of cosine theta divided by 1 plus sine theta d theta. So a good tip for me is when I look at the denominator and I take its derivative, I get the numerator. So that right there makes the denominator a good choice for you, right? This again, you need to do u substitution because we're trying to transform it into an integral that's more manageable. And so I'm going to let u be 1 plus sine theta. Okay? Du is cosine theta d theta. And this is the integral. Now, the denominator became u. Now, cosine theta d theta is another name for du, right? So I'm going to integrate 1 over u du. But this is natural log of the absolute value of u plus c. Okay, you don't want to take the natural log of a negative number, and it could be negative, so we have to take absolute values. But remember, u is 1 plus sine theta. So this is natural log of the absolute value of 1 plus sine of theta plus c. That's how we do 17. Let's take a look at 20. Suppose I have the integral of e to the negative 5r dr. So I'm going to let u equal, so negative 5r is a good candidate for u. This takes some experience, it takes some practice, okay? Now, du is negative 5 dr. So if I get dr, I'm going to divide both sides by negative 5. So dr is negative 1/5 du. Now I get to put everything back in terms of u. So this is negative 1/5, the integral of e to the u du. Now, the integral of e to the u is e to the u plus some constant. So we end up getting negative 1/5 e to the u, right, plus c. But remember that u is negative 5r. And so this is negative 1/5 e to the negative 5r plus c. And that's how we do problem number 20. Let's take a look at problem number 23. So on 23, this one's a little interesting. We got the integral of a plus bx squared divided by the square root of 3a plus, this is 3ax plus bx cubed dx. Now, the inside function is what's inside the radical. And that's usually a pretty good choice for you, right? Remember, your goal is you're trying to transform an integral in terms of x into an integral that's in terms of another variable, right? And so I'm going to let u equal 3ax plus bx cubed. So if I want du, this is 3a plus 3bx squared. Okay? Now, you might think, well, if I look at the numerator, that don't look like du, right? And by the way, we need to attach a dx here. Okay, that's important, by the way. That notation is very important. Okay, and you can see I attach a dr, right? So when I differentiate, r becomes dr. If you go back to 17, when I get du, it's cosine theta d theta. So we do have to have a dx. Now, so what I'm going to do is factor out the 3, and I get a plus bx squared dx. So I'll be darned. I can solve for a plus bx squared dx by dividing both sides by 3. So a plus bx squared dx is 1/3 du. And so this is 1/3 the integral of 1 over square root of u du. But this is 1/3 the integral of u to the negative 1/2 du. Now remember, negative 1/2 plus 1 is a half, right? And so this is 1/3 times 1 over a half u to the half plus c. Okay, and I'm gonna do this. Now, when you divide by a fraction, you multiply by the reciprocal. And so this is 1/3 times 2u to the 1/2 plus c, right? Yep. And u is a plus bx squared. And so this is 2/3 times a plus bx squared to the 1/2 plus c. And that's how we do 23. Let's take a look at 26. Suppose I had the integral of sine x times sine of the cosine of x dx. It's another classic u substitution problem, and it looks a lot worse than it is, right? You want to look for an inside function as a candidate for my u, right? And the inside function in this problem will be this cosine of x. And so I'm going to let u equal cosine of x. So if I want du, I get negative sine x dx. Now, if I solve for sine x dx, right, I get negative 1 du, right, or negative du. So I'm going to pull a negative on the outside, and I'm going to take the integral of sine u, right, du. Because sine x dx with that negative becomes, well, basically I get sine x dx becomes negative du. So negative goes on the outside, and I'm integrating sine of u du. Cosine of x became my u, okay? And so this is negative of. Now remember, the function whose derivative is sine of u is negative cosine u. So I'm going to put a negative cosine of u there, and then I'm going to add c. But u is equal to cosine x. So this is cosine of x plus c. That's how we do problem 26. If we take a look at 29, we get the integral of x minus 1 over x squared times x squared plus 2 over x to the 5th power. This is a fantastic question. This is a great question. The reason why is because the author doesn't want you to take x squared plus 2 over x and raise it to the 5th. Take that answer and multiply by x minus 1 over x squared. They are trying to get you to see that it's more beneficial to do u substitution. Okay? Now, the inside function is going to be x squared plus 2 over x. And that's a great candidate for u. Okay? So when I do du, I get 2x minus 2 over x squared in parentheses dx. So recall that the derivative of 1 over x is negative 1 over x squared. So that's where I'm getting the second line. So I'm going to take and factor out a 2. And so du is 2 times x minus 1 over x squared dx. So x minus 1 over x squared dx. And then I'm going to divide both sides by 2, so I'll write 1/2 du. And so I'm going to pull a 1/2 out of the integral, and I'm going to take the integral of u to the 5th du, which is 1/2 times 1/6 u to the 6th plus c. But u is what? X squared plus 2 over x. And so this is 1/12 times x squared plus 2 over x raised to the 6 plus c. That's how we do problem number 29. If we take a look at problem 32, this is a great question too. So if I have e raised to the arc sine x divided by the square root of 1 minus x squared dx. Now, one thing we have to pay attention to, right? Now, the inside function is going to look a little different here because I recognize what I'm saying is in the previous examples, I would let u be 1 minus x squared, and I would find du and go from there, right? The problem with letting u be equaling 1 minus x squared, I'm not going to transform that entire integral in terms of u. But I do remember that if I take the derivative of arc sine x with respect to x, I get 1 divided by the square root of 1 minus x squared. So why is that important? Because that tells me that arc sine x is a good candidate for my u. So notice how the derivative is present in the integral. So when I do du, I get 1 over square root of 1 minus x squared dx. And so this is the integral of e to the u du, which is e to the u plus c. But u is arc sine x. So this is e to the arc sine x plus c. That's how we do 32. Let's take a look at 35. Suppose I have the integral of arc tan x to the second divided by x squared plus 1 dx. It's a similar idea to problem number 32. I just happen to remember, and this might be good for another video, if I take the derivative of arc tangent of x with respect to x, I get 1 over x squared plus 1. And that tells me that calling u arctangent of x is a pretty good candidate because, again, I'm going to stress again, you're trying to transform the entire integral in terms of u's. So du is 1 over x squared plus 1 dx. And so this is the integral of u squared du, which is 1/3 u to the third plus c. But remember, u is arctan x. And so this is equal to 1/3 times arctangent x to the third plus c. That's how we do 35. If we take a look at problem 38, suppose I had the integral of sine theta cosine theta divided by 1 plus sine squared theta d theta. Now, a good candidate will be the denominator. So I'm going to let u be 1 plus sine squared theta. Du is 2 sine theta cosine theta d theta. So that's just chain rule. Now, sine theta cosine theta d theta is 1/2 du. That allows me to put everything back in. So I get half the integral of 1 over u du, which is 1/2 natural log of the absolute value of u plus c. Now, remember u is 1 plus sine squared theta, which, by the way, is strictly bigger than 0. It doesn't matter what you put in for theta. That's always going to happen. So when I replace u with 1 plus sine squared theta, I don't need to have the absolute value bars. So the correct answer here is 1/2 natural log of 1 plus sine squared theta plus c. I hope that makes sense. I don't need absolute value bars because 1 plus sine squared theta is always, always, always going to be positive. And that was problem number 38. If we take a look at 41, and we'll make this the last problem for the video. Suppose I had the square root of cotangent theta times cosecant squared theta d theta. And so I'm going to let u be cotangent theta, right? That's a good candidate because I know that the derivative of cotangent theta is negative cosecant squared theta, right? And so the derivative is almost present in the integral. It's just offset by a constant. So when I get du, I get negative cosecant squared theta d theta. So cosecant squared theta d theta is negative du. And that allows me to put everything in. And so this is the integral with the negative on the outside of the square root of u du, which is negative the integral of u to the 1/2 du. So this is negative 1 over 1/2 plus 1 u to the 1/2 plus 1 plus some constant c. But 1/2 plus 1 is 1.5. It's just a mixed number, which is 3/2. And 1 divided by 3/2, when you divide by a fraction, you multiply by the reciprocal. So this is 2/3. And so this is negative 2/3, u to the 3/2 plus c. But u is equal to, let's go back. U is cotangent theta. So I'm done. So this is equal to negative 2/3 times cotangent theta to the 3/2 plus c. And that will conclude this video for section 5.5, and we worked on problems 14, 17, 20, 23, 26, 29, 32, 35, 38, and 41. Thank you.